So here's a little review from exam 3. And in particular, we're starting here by looking at question 2 from the test. And we were asked to solve for x given this beautiful rational function or rational expression. So looking at this, we want to get rid of these fractions. Nobody likes a fraction, so we want to get rid of them. So the first thing that we need to do is find that least common denominator, so that LCD. So looking up at our given expression here, in this first denominator we have the factor x minus 3, so that has to be part of our least common denominator. Looking at the second term here, we see we have a factor of x, so that also has to be part of our least common denominator. And on the right-hand side of the equal sign, we have a quadratic. We notice that this has a greatest common factor of x, so if we factor that common x out, we're left with x times x minus 3. Hey, and that's what we have here. So this x times x minus 3 is going to be the least common denominator that we'll want to multiply both sides by to remove those fractions. And now, before we do that, let's keep in mind that we know that rational functions or expressions are undefined when the denominator is 0. So we know that rational functions do not exist or are undefined if the denominator is 0. So to make sure that we don't get any extraneous solutions, let's go ahead and set this least common denominator, this x times x minus 3, equal to 0, and solve for x. And so we have two cases here. We have x is equal to 0, and then in case 2 we have x minus 3 is equal to 0, and solving for x, we can add 3 to both sides of the equation, and 3 minus 3 goes to 0, leaving us with x equals positive 3. So we want to be on the lookout for these two x values in our final answer, because these do not exist. They're going to make that original function undefined. So now that we know what to keep a lookout for and that we have our least common denominator, let's go ahead and remove those fractions. So we want to multiply both sides of the equation by that LCD. So we're multiplying both sides by x times x minus 3. So we want to make sure that we leave ourselves plenty of room. So I'm just rewriting this given expression first. I have 3x divided by x minus 3. And then that would be minus 4 divided by x. And that's equal to 12 all divided by x times x minus 3. And so we are multiplying both sides of this expression here by the LCD. So multiply both sides by x times x minus 3, x times x minus 3. And we can see right away that the two factors, that least common denominator and the denominator on the right-hand side, those guys cancel each other out right to 1. However, on the left-hand side here, we want to be mindful that we need to distribute this least common denominator through to both terms. So we can rewrite this as x times x minus 3, and that is multiplied by 3x all divided by x minus 3. And then this will be minus, then we have that LCD x times x minus 3 multiplied by 4 divided by x. And that's all equal to 12. And so now that we've distributed that, we can see the x minus 3 in the numerator canceling with that x minus 3 in the denominator of that first term. In the second term, we see the x in the numerator will cancel with the x in the denominator. And so this leaves us with x times 3x minus, I'm going to write this as 4 times x minus 3 is equal to 12. And so now we can start simplifying. Now we have what looks like a linear expression here. It looks far more familiar. So with this first term, we have x times x. So this gives us 3x squared. And then with a second term, we want to be sure to distribute the negative 4 through to both pieces in that binomial. So this becomes minus 4x. Then we have a negative 4 times negative 3 for a positive 12. And that's equal to 12. And so in order to solve here, we want to bring all of the terms to one side. So I'm going to subtract the 12 from both sides of the equation. And conveniently enough, they're going to cancel each other right out. So they both go to 0. And we are left now with 3x squared minus 4x is equal to 0. And we can factor here. We have a greatest common factor of x. So I'll pull that x out, which leaves us with x times 3x minus 4 is equal to 0. And we can apply that 0 factor property and think about both cases. So we have x is equal to 0. And then in case 2, we have 3x minus 4 is equal to 0. We can add this 4 to both sides of the equation. So those 4's cancel each other out. And we have 3x is equal to 4. And last but not least, to isolate that x, we'll divide both sides here by 3. So 3 divided by 3 goes to 1. And so our second possible solution is 4 over 3. And now I say possible solutions because we don't want to forget what values made the original function undefined. And so we can see here, this first case, x is equal to 0, matches one of our solutions. So we know that this cannot happen. That's an extraneous solution. So an extraneous solution, it's undefined. It's a false conclusion. Now with the second case, x equals 4/3 is fine. So this is going to be our beautiful final answer. And so here we're going to go ahead and look at question 6 from the test. And now question 6 is asking us to find the zeros of the given function algebraically and then state their multiplicity. We're then going to want to use this multiplicity for each factor to determine the graph's behavior at each of the zeros. And we are given the function f of x is equal to x squared plus 12x plus 32, and all of that is squared. So the first thing we want to do is find the zeros. So to find the zeros, we know that we're going to need to set that given function f of x equal to 0 and solve for x. But we want to be careful here when solving, right? We know we want to find the multiplicity of each factor. So that means we should factor when we're solving this to find these zeros. So let's actually think about our polynomial before we start solving here. And to make this even a little nicer, easier to see, I'm just going to think about the inside here. So taking out that inside, we have x squared plus 12x plus 32. And we want to factor this. So I think to myself, okay, what two numbers multiply to give me 32? Positive 32. So what two numbers multiply to 32? And those same two numbers need to combine together to equal 12. So, and combine to 12. So what two numbers multiply to 32 and combine to 12? And I use the word combine here because we don't know normally if it's going to be addition or subtraction. Now here with this example, notice that we only have positives, right? So we can actually replace the word combine with add. But that's not always the case, so just be careful. So thinking about the factors of 32, we know that 32 is equivalent to 4 times 8. So that works. Now let's check the sum of those two. So we know that 4 plus 8 equals 12. Woohoo! So those two factors are going to work. That means that this polynomial expression here is equivalent to x plus 8 times x plus 4. So now that we've done our scratch work, let's plug this back into our function and think about what's going on. It's going to give us a little more room. Don't want to lose that scratch work too fast. So again, we were given f of x is equal to, we had x squared plus 12x plus 32 squared. So now we can give ourselves more room. And we just did the scratch work to factor that inside there. So we know that this is equivalent to x plus 8 times x plus 4, and that's all squared. So now, by the properties of exponents, we can take this square and distribute it to each one of these factors. So our function f of x is redefined now as x plus 8 squared times x plus 4 squared. And so we leave it like this simply because now we can see the factors that appear. Right, we'll make a little note to ourselves here before we finish solving. We have two factors. We have a factor of x plus 8, and we think to ourselves, well, how many times does this factor appear? It appears 2 times. So that means if it appears twice, it has a multiplicity of 2, which is even. And we also look up at our factored function, and we see this also has a factor of x plus 4. A factor of x plus 4. And again, we think to ourselves, how many times does this factor appear? It appears 2 times. So this also has a multiplicity of 2, which again is even. So multiplicity is how many times does this factor appear? Because we could, if we really wanted, we'll have to give ourselves a little more room. If we really wanted, we could say that this polynomial is equivalent to x plus 8 times x plus 8 times x plus 4 times x plus 4. And now we can really see that each one of these factors is appearing 2 times, as we've determined here. But it's going to always be nicest to keep it in this form. It's a little more compact, but they're both the same. So now that we've gone through this and we've actually already determined the multiplicity, because both of these have a multiplicity that's even, we know that the graph is going to be tangent to the x-axis at the 0 associated with each one of these factors. So let's find the zeros. We haven't done that yet. So we want to find the zeros for each factor. So we have a factor of x plus 8 is equal to 0. And solving for x, if we subtract 8 from both sides, the 8's will cancel each other out, leaving us with x is equal to negative 8. And we can write this as an x-intercept, negative 8, 0. We also have the factor x plus 4, and we're solving that, setting that equal to 0. And if we go ahead and subtract 4 from both sides of the equation, the 4's cancel each other out, and we're left with x is equal to negative 4. We can write this in the x-intercept form, negative 4, 0. So these are our zeros. And we can make our final conclusion here and say that therefore, since both factors have an even multiplicity, or since both factors have a multiplicity of 2, we know that the graph will cross the x-axis. Excuse me, shame on me. The graph is tangent to the x-axis at these zeros. So it's tangent to the x-axis at x equals negative 8 and x equals negative 4. And so that is our beautiful final answer.